Okay, good morning, chemistry students. Wanted to talk to you guys today. Sometimes it's hot, sometimes it's cold, and sometimes you got to learn a little bit about exothermic and endothermic reactions. Got my jacket on here, so maybe we'll start off with a little endothermic reactions. Um, so hopefully you watched the videos yesterday where with the two cool reactions, the endo and the exothermic. We're going to dig into those a little bit deeper today and understand why those are reactions that give off heat and reactions that absorb heat. So let me go in here and share a screen. These are the notes that you should be able to access on Canvas. And it takes a moment for my window to pop up over here, so give it a second. Okay, so chemical bonds store potential energy. We talked about energy yesterday. And as chemical bonds are broken or formed, energy is transformed back and forth between the surrounding environment and the chemical bonds. So two things you need to kind of keep in mind here. The system is what you're studying, all right? And so usually, you think about sort of what's in the container, whatever the chemical or whatever the reaction that's occurring, that's your system. And so energy can either come out of the system or it can go into the system, all right? And so the system is what you're interested in studying, and the surroundings are literally everything else. It's the entire universe. It's everything that is not the system. So just some language there to give you a little bit of a background. We're going to be talking about energy going into and out of the system from the surroundings. All right, so let's talk about the two different types of reactions here. Reactions can be classified depending on whether or not energy is going into the system from the surroundings. And if you think about this, if I am giving energy to a system, all right, so the reaction is some sort of reaction that absorbs energy from its surroundings, all right? The surroundings are going to get colder because the surroundings are losing energy. And as it loses energy, all the particles start to move a little bit slower. And so the keys here, endothermic reactions, right? They're going to cause the surroundings to get colder, and they're going to be represented with a delta H, a change. Delta is the symbol for change. Change in heat, that is positive, all right, because it is a gain of energy. So it's a little bit tricky for some students, all right? Even though it's colder, which you're kind of like, well, the temperature is dropping, so wouldn't that mean a negative sign? Get that right out of your head, all right? Endothermic reactions are taking energy from the system. And so we're going to do a couple of things here. I'm going to show you some diagrams in just a minute and some reactions. Exothermic reactions, on the other hand, are totally different beasts. Those guys, when the chemical reaction occurs, they create energy, all right? And so these are going to give energy to the surroundings. And so the system itself is going to be giving off energy, which means that when you are near an exothermic reaction, it's going to feel hot because it's giving energy to the surroundings. So you're gaining heat. You're gaining energy from that reaction. And so it feels hot. And the change in heat, all right, it is losing energy. So we're going to say that that is going to be a negative sign in front of the energy term there. All right, so that's the first page. Let's go ahead and look at the second page here. And we're going to focus in on the two different types of reactions. Sorry about that. And I'm going to cough here. See if I can mute it before I cough right in the microphone. I don't know if I'm going to catch it. Okay, so I think we're back. All right, so let's talk more about an exothermic reaction. We can write exothermic reactions, or we can represent exothermic reactions in a couple of different ways. Let's see if I can get some water here. The first is using just our old-fashioned, when we write a chemical reaction, Notice that we have this term over here, and we talked yesterday about energy units. This would be kilojoules, which is literally thousands of joules. So when this guy happens, all right, and this is a thermite reaction. We're going to take some iron oxide and some aluminum, and it makes some iron and aluminum oxide and what appears to be if you recall, this would be a single replacement reaction. Uh, this is also producing energy. So since energy is being given off, since energy is released in an exothermic reaction, we're going to put the energy term as a product. So that means that it's going to be over here on the right-hand side. So if you see this energy term, this unit of energy popping over here as a product, it's definitely an exothermic reaction. So if we were to put a temperature probe or thermometer on this type of reaction, we would see a large increase in temperature, or maybe not large, but it would be an increase in temperature because as the reaction proceeds, energy is given off. Now, the other thing that I want you guys to be comfortable with is what we call an energy diagram. And these are tricky for kids sometimes, so let's just walk through those real quick. Excuse me. So notice what's on the y-axis. We've got potential energy, all right? This is the energy that's stored up in the chemical bonds, all right? And reaction pathway, another word for that is just kind of time. As the reaction proceeds in this direction, time is moving in this direction. So at first, the reactants have a certain amount of energy. So this right here, all right, well, actually, I'm going to draw on this a little bit. So this right here, all the way from the bottom to the top, that would represent the total amount of energy in the reactants, because energy is what's on the y-axis. And so we're saying that the reactants have 150 kilojoules of energy right now. Now, for a reaction to occur, there's always a little bit of a barrier, okay? And this barrier is much like the hill that you have to get up when you're going up a roller coaster. The roller coaster isn't very much fun until you have been dragged up to the top of that hill. And then once you get to the top of the hill, the roller coaster is ready to roll and we get the ride. So this guy right here is what we call, it's a little bit of a barrier. And I'm going to go ahead and draw this in, and it's already labeled over here as B. All right, but this is a really important thing, or excuse me, it's labeled as A, it looks like. I'm sorry, I couldn't see that. And that is what we refer to as the activation energy. It's the energy needed to get the reaction started, right? So this one's telling me, look, I've got to put 50 kilojoules of energy in. Maybe you have to heat the reaction up. Maybe you have to have some friction that creates that heat. But in some form or fashion, this particular reaction, in order for it to occur, you've got to put in 50 kilojoules of energy. Now, once you put in that 50 kilojoules of energy, that unleashes, look at this. Oh my gosh, we're going to go all the way from what was 150. We put in 50 to get out the ride. And so our products end up at a lower energy state than our reactants. And that's the hallmark of an exothermic reaction. Reactants have more energy than products. Because remember, we gave off energy, so the reaction lost energy. It's a delta H that was negative, right? We had our energy term showing up over on the product side of things. And so we come over here and we say this we called the activation energy, all right? Now, up here at the tippy top before we do the reaction, right? The reactants have all gotten themselves ready to react and they're just about ready to react. That's called the activated complex. It's an intermediate form that must form for the reaction to proceed to the products. And I do expect you to know that term here, okay? The activated complex is when basically all the bonds of the reactants have broken and they are just ready to start putting themselves together into the form of the products, but they haven't yet. All right, so now we come over here and we drop all the way down. So this difference, the difference in energy between the reactants at 150 and the products over here at 50 kilojoules, that would represent the amount of change in heat, the amount of change in energy. So this guy lost 100 kilojoules worth of energy. So this would be exothermic to the tune of negative 100 kilojoules. That is what we call an energy diagram. So this would be the energy of the reactants, right? This right here would be what we call the activation energy. If I wanted to know how much energy the activated complex had, I just go, hey, look, let's go all the way up to the tippy top here. That would be the energy that we have at the activated complex. If I want to know how much energy the products had, that would be this value right here. And then last but not least, the change in energy is going to be that difference between what we have energy-wise at the reactants, 150, versus the products at 50. That's an exothermic reaction there, guys. Now, let's switch it up, and let's turn this guy into an endothermic reaction. Now, I got my jacket on, endothermic. Endothermic absorbs energy from the surroundings, which makes the surroundings colder, right? So if you think about this, if I'm going to absorb energy, that means that the energy had to be there at the beginning. It's literally like a reactant. So if I am an endothermic reaction, I'm going to absorb energy and I'm going to show up as a reactant term, all right? And that's what you see in this particular example. Without that energy term here, I'm not going to end up making my products. These ones are going to feel cold, and we already said that they're going to have a delta H that is positive. So let's look at the energy diagram for a endothermic reaction. Again, potential energy. The energy stored in the chemical bonds is on the y-axis. Reaction pathway is along the x-axis. This is time. So if I asked you, how much energy do the reactants have at the beginning? You'd look and say, okay, the reactants are sitting at 100 kilojoules of energy. If I asked you, what is the activation energy? How much energy does it require to make this reaction occur? That's a pretty big hill you got to get up and over. You've got to go from 100 all the way up to 400 units of energy. So the activation energy, it would require 300 kilojoules of energy to get this reaction to occur. Here's the activated complex. These are the intermediaries that form just before the products go. You'll notice this is a little bit of a, it's not as much fun of a roller coaster. You put in all of this time climbing this big hill and you whoop, get this tiny little hill. So endothermic reaction, you have to put in a ton of energy, right? We started out at 100 and all we get down to is 300. So we had to put in a total of 200 kilojoules of energy. So the delta H, the change in heat, right, is going to be a gain of 200 kilojoules. The activation energy would be from 100 to 400. So the activation energy would have been 300 kilojoules, right? And let's see, what else do we need to know? The amount of energy that the reactants had would be 100. The amount of energy that the products had would be 300. And then one last thing. Let's say if we wanted to consider the reverse of this reaction. The reverse of this reaction would make the products be over here, and then the reactants would be over here. And we would just have to kind of mentally flip this. And instead of going from left to right, we'd be going from right to left. So if you look at this, the reverse reaction, if we could somehow make the products become the reactants and the reactants become the products, whereas it was a endothermic reaction going in this direction, this looks like we've got a large amount of energy going to a smaller amount of energy, which looks like an overall loss. So hopefully you can see that the reverse reaction here would be an exothermic reaction. Guys, that is the essence of what I wanted to get to you all about different types of reaction, whether they be exothermic or endothermic. So in summary, excuse me, for endothermic, just remember that endothermic, the energy term, energy is a reactant. I'll get my hand out of the way in a second. Energy is a reactant. that the delta H is going to be positive, and that the picture of these are going to start down low and they're going to end up high. All right. Exothermic, and excuse me, I guess we can say endothermic, are going to feel cold. Exothermic, right? This is where the energy term is a product. A delta H, the change in heat, is going to be negative because you're losing energy to the surroundings. These guys are going to start out up high. You got to get up and over the hill, and then you're going to start down low, and these are going to feel hot. Sorry that took a little bit longer than I was hoping, but hopefully it's still not too painfully long. Let me stop sharing and wish each of you a wonderful day. And hopefully I get to see you guys in class. We're running classes at 9 a.m. We're about 9 to 9:30 or so every other day. So check the Canvas schedule and see if you can catch a class. I've got office hours each day this week, Monday through Friday, from 10 to 11:30. Those are just drop-in times where you can come and ask questions or catch up. So hope to see you soon. Take care. Bye-bye.